this video, we will look at what we mean by the terms metal, non-metal, and metalloid, as well as exploring the properties of each of these. Let's start by looking at the periodic table and working out where we can find metals, non-metals, and metalloids. Here we have a rough outline of our periodic table. Generally speaking, metals can be found on the left-hand side of the periodic table, while non-metals are on the right-hand side. Hydrogen, however, is an exception. Even though it's found on the left-hand side, we would consider hydrogen as a non-metal. The next question is, where do these two sections meet? The border between metals and non-metals is often drawn on the periodic table as a stepped line. It works its way down between boron and aluminum, silicon, germanium, arsenic, antimony, and tellurium. However, the elements either side of this border aren't necessarily easy to classify. And this is especially true the further down the periodic table we go. Elements such as boron, silicon, germanium, arsenic, antimony, and tellurium can exhibit properties of both metals and non-metals. So we might classify them as metalloids. Sometimes they might be referred to as semi-metals. You can think of metalloids as partway between a metal and a non-metal. Now that we know where to find metals, non-metals, and metalloids, let's have a look at the properties of each of these. To understand the properties of metals, we need to remind ourselves about metallic bonding. The atoms in a metal are arranged in this regular crystalline lattice shape. In between this, we have a sea of delocalized valence electrons. These delocalized electrons can flow throughout the lattice. It is this specific structure which can lead to some of the properties of metals. The first key property of metals is that they are hard. The reason that metals are hard is due to the strong metallic bonding. That is, that the electrostatic attraction between the positive nuclei and the negative sea of delocalized electrons is very strong. This makes it difficult to break this structure apart, leading to metals being hard. Metals also exhibit a high density. Having a high density means that a substance has a high mass for the size or volume that it is. Metals have a high density because they have a large number of atoms packed very closely into a small space. Metals can also be polished to make them shiny. When we polish a metal, we make the surface incredibly smooth, and the shine produced is caused by the interaction of light with the sea of delocalized electrons. You might hear this metallic shine referred to as a luster. Metals are also ductile. If a substance is ductile, it means that it can be successfully drawn out into a wire. The reason that metals are ductile again comes down to the structure. When we apply a force to a metal in order to draw it out into a wire, for example, the layers of atoms can slide over one another, allowing it to be drawn into this wire. This movement of layers is the same reason that metals are malleable. Malleable means that something can be shaped by hammering, and this is the case with metals. Metals can also be sonorous. This means that they make a sound when struck. Think about striking a metal bell, for example. And perhaps one of the most important properties of metals is that they are electrically conductive. This means that they allow the flow of an electrical current through them. This is made possible by the sea of delocalized electrons. When a voltage is applied to a metal, this sea of electrons can flow through the material, meaning that it can carry the current through a wire, for example. There are, of course, always exceptions to all of these properties. Take, for example, mercury. Mercury has a particularly low melting point, which makes it a liquid at room temperature. This is, of course, incredibly unusual for a metal. Now that we've summarised the properties of metals, let's compare these to nonmetals. The properties of nonmetals are very different to those of metals. For example, we've seen that metals are hard. In contrast, the majority of nonmetals are soft. Just like we did for metals, we can understand many of the properties of nonmetals by looking at their structure. However, this is slightly more complicated for nonmetals. Among the elements in the non-metal category, we have a huge range of different structures. Non-metal structures tend to involve covalent bonds, in comparison to metals which have metallic bonds. Some nonmetals are also made up of individual molecules. Think about oxygen as a gas, for example. Moreover, in nonmetals, the electrons are generally localized, unlike in metals where they are delocalized. In fact, nonmetals can form a variety of different states. For example, the noble gases are all gaseous, bromine is a liquid, and something like sulfur is a solid. So we have quite a range of different structures. This also means that when we compare the densities, metals have a very high density because they have lots of atoms packed into a small space, but nonmetals have a much lower density. We saw that metals can be ductile and malleable, but in the case of nonmetals, thanks to their structure, they are often brittle. Brittle means that if you try to deform a nonmetal, it will break. While metals are electrically conducting, nonmetals are the opposite. They are electrically insulating. This means that they do not allow electricity to pass through them. This is because their electrons are localized instead of delocalized. Again, though, there can be exceptions. For example, carbon in the form of graphite. In graphite, the structure, just like metals, involves layers. Each layer is made up of carbon atoms which are covalently bonded to 3 other carbon atoms. In between these layers, though, we do have some free electrons. And it's these electrons which allow carbon in the form of graphite to also conduct electricity. So far we've seen that metals and nonmetals tend to be opposites when it comes to comparing their properties. But what about those metalloids? Remember that metals tend to be found on the left-hand side of the periodic table, and nonmetals are found on the right-hand side. And metalloids can be found either side of the stepped line where metals and nonmetals meet. Metalloids tend to display properties of both metals and nonmetals. So if metals conduct electricity and nonmetals insulate, what do metalloids do? The answer is something in between. We refer to metalloids which exhibit this in-between property as semiconductors. Silicon, for example, is a very commonly used semiconductor. We can even make semiconductors more efficient at conducting electricity by heating them up. In contrast, if you heat a metal, it reduces the amount of electrical conduction. Other uses for metalloids include solar cells, catalysts, and as fire retardants. Now that we've explored the properties of metals, nonmetals, and metalloids, let's have a go at some questions. Which of the following statements does not accurately describe a comparison between nickel and sulfur? A. Nickel has a higher melting point than sulfur. B. Nickel is denser than sulfur. C. Nickel is softer than sulfur. D. Nickel is stronger than sulfur. Or E. Nickel is more ductile than sulfur. We're being asked to compare the properties of two elements, nickel and sulfur. So let's start by working out where these two elements are on our periodic table. Nickel can be found in the D block in the middle of the periodic table, while sulfur is found closer to the right-hand side. Remember that on the left-hand side of the periodic table we find metals, and on the right-hand side we find nonmetals, with the exception of hydrogen, of course, which is a nonmetal. We can see from this that nickel is a metal, while sulfur is a nonmetal. So what this question is really asking is for us to compare a metal with a nonmetal. The question is also asking for the one statement which does not accurately describe a comparison between a metal and nonmetal. This means that we can expect 4 of our potential answers to be true and 1 to be false. And it's this false answer which is the correct one. So let's start with A. Nickel has a higher melting point than sulfur. The properties of a metal or nonmetal are often due to the structure. So let's remind ourselves of the structure of a metal and nonmetal. A metal is made up of a closely packed, regular lattice of atoms. In between these atoms, there is a sea of delocalized electrons. Nonmetals have much more varied structures. They tend to involve covalent bonds and sometimes individual molecules. They also tend to have localized electrons as opposed to the delocalized electrons in a metal. But how does this relate to the properties of our metal and nonmetal? The attraction between our positively charged nuclei and our negatively charged sea of electrons in a metal makes metallic bonding very strong. Because this structure is so strong, if we want to melt it, for example, we need an awful lot of energy. Because metals need a lot of heat to melt them, they have high melting points. Remember as well that nonmetals often have the opposite properties of metals. Because the structures of nonmetals tend not to be anywhere near as strong as a metal, they have much lower melting points, since it takes a lot less energy to melt them. In fact, some nonmetals are even gases at room temperature. For example, oxygen. So answer A says that nickel, a metal, should have a higher melting point than sulfur, a nonmetal, and we've discovered that this is true. This means that A is not the correct answer. Let's move on to B, that nickel is denser than sulfur. Density is a measure of how much mass there is in a certain volume. Metals have a closely packed, regular lattice structure of the atoms. This means that they have a high density. Nonmetals, on the other hand, don't always have lots of atoms in a small space, and nonmetals tend to have a low density. So the statement that nickel, a metal, has a higher density than sulfur, a nonmetal, is true. So again, this is not the right answer. Statement C says that nickel is softer than sulfur. We've already seen that the metallic bonding in nickel is very strong, while the bonding in nonmetals is much weaker. This makes many nonmetals very soft. So the statement that nickel, a metal, is softer than sulfur, a nonmetal, is false. So this is a correct answer, but let's check the last two statements just to be safe. D says that nickel is stronger than sulfur, and we've already seen that this is true. Metals are stronger than nonmetals. So D is incorrect. Statement E says that nickel is more ductile than sulfur. The word ductile means that a substance can be drawn out into wires. Metals are often ductile, again because of the structure. When you apply a force to a metal, the layers of atoms can slide over one another, and this allows them to be drawn out into wires. This is the same reason that metals are malleable as well, where malleable means that a substance can be hammered into shape. So the statement that nickel, a metal, is more ductile than sulfur, a nonmetal, is true. Nonmetals are not ductile. They are, in fact, brittle, which means that if you try to deform them, they break. So the only false answer, and therefore the correct answer to our question, is C. Nickel is softer than sulfur. Let's summarise the key points. Metals, found on the left-hand side of the periodic table, and nonmetals, found on the right-hand side, tend to have opposite properties. Metals tend to be hard, while nonmetals are soft. Metals are ductile, which means they can be drawn out into wires, and malleable, which means they can be hammered into shape. Conversely, nonmetals are brittle, which means that if you try to deform them, they break. Metals have a high density, while nonmetals have a low density. Metals can be polished to give them a luster, meaning that they're shiny, but nonmetals are dull. Metals are able to conduct electricity, while nonmetals cannot, and they are insulators. The structure of metals is really responsible for a lot of the properties in metals. This closely packed crystalline lattice of nuclei surrounded by a sea of delocalized electrons. And finally, we have the metalloids, which can be found along the stepped line which joins metals and nonmetals on the periodic table. Metalloids exhibit properties somewhere in between metals and nonmetals. For example, an element like silicon is a semiconductor. You can find metalloids like silicon in microchips and transistors.